The following program is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com.
Welcome back to Element 14 Presents. I'm Ben Heckendorn, former host of The Ben Heck Show. With me today is one of the new content creators, James Lewis, aka the Bald Engineer. How's it going today? What are you building?
Well, Ben, I've got this big bag of change, and I'd like to know how much is in there.
Rain Man could tell you.
So I'm going to use this coin counter to, well, count the coins.
Oh, cool. So you could put that on top of your change jar. So when you come home from work, you can just shove whatever quarters you have in your pocket into that and it'll say, you have $20.
Exactly. Now, the challenge is that I don't have a power outlet near where I keep my keys and stuff, so I'm going to turn this into a battery-powered project.
Okay, are there any challenges that you face while doing that?
There's two challenges. The first one is this thing draws like 50 milliamps while it's on, so that would burn up a battery pretty quick. And it's got a 12-volt solenoid, so I need to find a way to power that.
So you need something that basically only wakes up when it has to.
My plan there is to take an idea from this demo board that I have where you use capacitive touch or capacitive sensing to do proximity detection.
Oh yeah, because you don't actually have to touch capacitive touch sensor. You can actually get near it and it will trigger it. Oh, so what you want to do is you want it to wake up as your skin's coming close to the metal. Then it's fully awake by the time the coins go in and then it can start counting.
Yep, and then I'll go back to sleep.
Sounds very cool. Well, good luck with your project. I hope it goes well. So I guess I'm going to go back into my state of semi-retirement and I'll let you get started with your cool project. So yeah, let's see what James comes up with.
Amazing hacks. Inspired designs. Each week, Element 14 Presents brings you innovative projects using electronics, engineering, and more.
Now that Ben is retiring, maybe I can cash in on some of that sweet, sweet YouTube money. Here's what I've earned so far. Let's count how much there is. Well, that might look really cool, but it takes a lot of video editing. So instead, we're going to use one of these. It's a battery-powered coin counter. It gets activated by capacitive touch. It changes this into an easy job. Get it? Change? Here's the good news. This coin acceptor does the hard work of detecting what coin is being inserted. We'll talk about how to set it up in a little bit. Here's the bad news, or challenge. The place that I want to put the bank has no AC outlet. So the real trick is how do we run this off of a battery? It needs like 12 volts and 50 milliamps when it's idle. That kind of power would drain a battery in a matter of hours. So to avoid that, we're going to turn on the collector using some special technology. I'm going to run up to my lab. While I do that, why don't you check out this block diagram for the project. So far, I have only mentioned two pieces, the coin counter and the battery. We also need an Arduino to control the counter, keep track of the bank's value, and display that value on an OLED screen. My goal is to only turn on the coin acceptor while coins are being inserted. Now, I could add a switch, but then I'd have to remember to turn it off, which I'll never do. Instead, we'll use magic to detect when my hand is near. Well, electronics magic. We're going to use a proximity detection sensor based on capacitive sensing technology. For that, we'll use an MSP430 with TI's Captivate controller built in. Taking a step back, we have a bit of a voltage mess. The Captivate and OLED run on 3.3 volts. The Arduino runs on 5 volts, while the coin counter needs 12 volts. But all we have is this 3.7 volt lithium polymer. So here's what we'll do. The battery will power the MSP430 through a diode. An Adafruit power booster provides 5 volts to the Arduino and gives us a way to recharge the battery. The Arduino's onboard regulator will power the OLED screen. It will also control a 5 volt to 12 volt boost converter for the coin acceptor. Speaking of which, that is the first block I want to discuss, so let's head to the bench. This particular coin counter can be programmed to recognize up to 4 coins. Programming or setting up the module is easy. You tell it how many coin types you want to detect, how many example coins you will use to train it, how sensitive it should be, and the number of pulses for the output. Then for each coin type, you insert 20 coins. This trains the detector. I found it to be very effective. Boring, but effective. Now this brings us to the output. The counter outputs pulses based on what we set. For each coin, you can get between 1 and 50 pulses. So my first thought was, why don't we do 1 for a penny, 5 for a nickel, 10 for a dime, and 25 for a quarter? Let's look at the scope and see why that's a problem. I put in a nickel, and we get 5 pulses. Now I'm going to save this into a reference waveform. Copy number 1, but turn it off and close it. And now I'm going to put in a dime. So we get 10 pulses for the dime. If we compare the two waveforms by using a reference function, we can see that they are very uniform. So that's good. But there's a problem, and it's most apparent when I put in the quarter. Watch. The quarter takes 3.5 seconds to get the pulses through. So if we put 2 coins back to back, we're going to get a very long pulse train. Let me show you with a quarter and a dime. Quarter and a dime. If you aren't familiar with a scope, let me explain something about time. The time per division is how long the scope looked at the signal for each of these grids or divisions. There are 12 of these, which means this screen is showing 6 seconds of time. So 25 pulses take so long that I can insert multiple coins. But if you look at the pulse train, the counter doesn't show us anything different between the coins. It just keeps outputting pulses with the same period or time between pulse. So looking at this waveform, is it a dime and a quarter? Or is it 2 nickels and a quarter? Or is it 5 nickels? So what do? Well, I decided 2 things. First, I don't really care about pennies. I usually leave them at the store anyway. Next, I decided not to track the coin type being inserted. Instead, I only track the total value of the coins. The counter has a built-in frequency divider, so I set mine to divide by 5. Now this means when we put in a nickel, we get 1 pulse. When we put in a dime, we get 2 pulses. And when we put in a quarter, we get 5 pulses. Every pulse we see on the scope is worth 5 cents, even if we see coins are inserted back to back. Now you might notice my scope can count the number of pulses, but if I go into the measurements, there's no measurement for money. Well, I guess we'll have to use an Arduino to handle that. Here's the basic code for interfacing to the counter. I'll provide this along with the final, which is just a little more complicated. For an Arduino, I'm using a Pyramidduino. It's a custom board I designed that's like an Nano without a serial chip, except that it's in the shape of a triangle. Connections to the counter include 12 volts, which we'll talk about in a bit, ground, and the count signal. The count signal is open collector. That means it doesn't matter if the microcontroller's voltage is 3 or 5 volts. The Arduino's built-in pull-up resistor will pull the signal to 5 volts when it is high. Down in the loop, I'm using this state change detection to tell when the pulse changes. When this if statement is true, the counter signal changed. So if it is high, then that means the pulse went from a low to high, and we increase the coin count. These 3 variables are a bit of housekeeping. They let us print an updated bank value and to update the EEPROM only after the last pulse goes through. You see, this millis check only allows the print to happen once per second, while this millis check prevents the EEPROM from being written on each pulse by waiting until the pulses stop. Turns out this is really not needed because EEPROM.put does the same check, but for EEPROM I don't mind doing a double check. Now when we put coins in, our serial monitor updates. So we've got the counter block done. Let's go talk about how we're going to power this coin acceptor. The coin acceptor needs 12 volts. The reason is that there is a solenoid or relay inside of the collector. Normally, coins just fall through to the return. When a valid coin is detected, the solenoid opens to drop the coin into the bank. The problem is that our battery only provides 3.7 volts. That means we need a boost converter. So I've designed a small module that can take voltages as low as 2 volts and boost them up to as high as 24 volts, depending on the resistors used. This one is set for 12 volts out. One thing to remember with boost converters is that by boosting up the voltage, we are also increasing the current on the input side. Normally measuring current means breaking the circuit, unless you have one of these guys. This is a current probe. We can use it to measure current on the oscilloscope. Here I'm measuring the converter's output signal to the coin acceptor. It's about 12 volts and it's drawing between 35 and 40 milliamps. You might notice that the DC signal isn't all that clean, but for a solenoid, it's clean enough. Now that I moved it over to the input side, we can see that the input is drawing 230 to 240 milliamps. In this case, I'm using my power supply, but if this was the battery, it would be dead in a matter of hours. That's why we're going to use capacitive sensing to turn the acceptor on and off.
The Hirschmann Spider 3 standard and premium line switches are designed for reliable operation in harsh industrial conditions. The Spider 3 also delivers increased performance and reduces your costs wherever you need Ethernet technology. It is easy to install and customize for specific applications through a USB port and an easy-to-use free software tool. The small size saves space in tight areas and makes installation simple and fast. Other features include high data throughput achieved by gigabit data speeds, while fiber communication options ensure long-term sustainability. Reduces overall life cycle costs with lower consumption. Flexible customization from 2 up to 26 ports. Enhanced network security by disabling unused ports. Learn more about the Spider 3 standard and premium line switches today.
Here I have a couple of boards from Texas Instruments. They both have an MSP430 microcontroller with a built-in capacitive sensing controller. This is the Boost XL pad and is an example of a capacitive touch panel with buttons. Now you can use this standalone, or you can connect it to another microcontroller over I2C. Originally, I wanted to use it in this build, but as I started to think about the enclosure, I realized I couldn't integrate this board. However, I do want to steal or borrow an idea from it. So let me demonstrate a key functionality. Get it? Key? I really need to stop with the puns. There are 2 LEDs on this board. One detects when you touch or push one of the virtual buttons. The other LED is the idea that I want to borrow. It's called the awake light. Notice as my finger gets close to the buttons, the panel wakes up. And it's because there's a guard band that goes all the way around the panel. So let's take this idea plus this board and a secret ingredient and add it to our prototype. Using this copper tape, I added strips to the front panel of our prototype. These create an electrode pattern similar to the Boost XL's guard band. Now you can see why I use clear for the prototype. When connected to the MSP, an electric field forms between these strips. By measuring the field and doing just a little bit of math, the controller knows the capacitance between the strips or, well, electrodes. When something conductive gets near the field, the capacitance changes. And it turns out that a hand is just conductive enough to affect the field so that we can detect its presence. By the way, I made a full tutorial on how capacitive sensing works, so check the notes for a link to that. TI's Captivate Design Center software helps in this case. I tell it that I'm using an MSP430 FR2633 and that I want proximity detection. Using auto configure, it tells me to connect to pins P0.0 and P3.0. In this case, polarity doesn't matter. We need to fine-tune the parameters for this particular sensor. There are some graphs that help show what happens as I interact with the field. On the tuning tab, we change the thresholds to detect proximity versus touch. Over on conversion control, we can adjust the sensitivity by increasing the conversion count. I won't go into detail about why I picked these numbers because they depend on your design, but at least you know which knobs to go and turn. As I move my hand back and forth, notice that the proximity indicator on screen changes from orange to green. With the sensors configured, I just export this to a project for TI's Code Composer Studio, which we'll get to later. At this point, you might be wondering, why am I using 2 microcontrollers? Do I really need both an Arduino and an MSP430? Well, okay, the MSP430 gives us both the capacitive sensor and ultra-low power modes, so I can connect it directly to the battery. I'm not as familiar with its architecture though, so that's why I decided to use it to turn on the Arduino through the power boost. That way I can do all the other stuff that I know how to do with an Arduino. More microcontrollers are better, right? That said, let's go take a quick look at the code for the MSP430. This code combines what the design center generated and what I added to control the power boost. These 4 lines configure the microcontroller. The cap app start function does a bunch of configuration for the cap touch sensor, or cap touch controller. It also configures the low power mode, which enables the 430 to deep sleep. That means only the cap touch controller is powered until it detects a change. When it wakes up, it checks to see if the proximity threshold that we already set was reached. If so, the power boost gets turned on, turning on everything else. The counter starts a timer to keep the rest of the system active while I'm inserting coins. About 15 seconds after my hand stops tripping the proximity threshold, the MSP turns off the power boost and goes back to sleep. Okay, so at this point, we have covered all the major blocks for the project. I have the Arduino controlling the coin acceptor through a MOSFET, which is also connected to the 12-volt booster and an OLED display. The Adafruit power boost is controlled by the MSP430. We already talked about the current on the coin acceptor. Now I want to look at the MSP430 and its sleep mode. For this measurement, I'm going to power it with my power supply, connect it to a multimeter so that we can measure the current. When the processor is sleeping, it draws between 20 and 130 microamps, which is about an average of 50 microamps. When it wakes up, it draws between 5 and 7 milliamps. Compared to the rest of the circuit, that's practically zero. With an average of 50 microamps, let's calculate how long this 500 milliamp hour battery would actually last. Back to the virtual whiteboard. Battery life is calculated as battery capacity divided by load current. Then we multiply by a percentage to account for efficiency. I'm using 80%, which is pretty conservative. Remember, our battery has a 500 milliamp hour capacity, and our circuit draws 50 microamps when it's asleep. After dividing these and multiplying by 80, we get 8,000 hours. Let's just say there are 31 days in a month, and then multiply that by 24 hours to get 744 hours. Rounding up to 750 and dividing 8,000 by that, we get 10.6666, 10 months. This system should be able to sit on my shelf for 10 months. That's pretty cool, huh? Okay, I'm getting tired of looking at all these wires, so I want to move on to the final enclosure, even though I have a few loose ends to tie up. Let's jump over to Fusion 360 real quick. Here's what the final enclosure will look like. Each of these panels will be laser cut out of acrylic. I'm using Fusion to make sure that they all fit together and that there's enough space inside for all of my electronics. If I remove this panel, you can see there's 2 shelves for the electronics, one for the MSP430 and one for everything else. I use this model to find where to put the holes on the back panel. I need the programming port for the MSP430 because we'll need to recalibrate the touch sensor once the enclosure is put together. The coins will drop into this drawer, which slides out like this. The drawer contains the only 3D printed parts of the project. The 2 slides on the bottom and then 1 on each side. Here's an example of the acrylic that I'll use. You'll notice that it already has this masking applied to it. One thing I'm going to be doing with the side pieces is laser engraving an outline. That way I can remove this tape and have a place to glue the rails onto and make sure that they're aligned correctly. Since we're talking about the 3D printed parts, let's jump to a time lapse so we can watch them get made. Well, I made that clip and I'll say it was not impressive. So I want to make it up to you. So instead, let's go watch a montage of the laser cutting and build of the final assembly. Let's get going. Shoot. Let's go. Okay, so I've put everything together into the final case and I've cleaned up the last few bits of code. I even added a reset with another capacitive touch button on the back. Pretty cool, huh? So in this build, we looked at how this counter works and how to program it with an Arduino. Then we solved the challenges of running it on a battery using TI's Captivate touch technology, which is found in their MSP430 series microcontrollers. Finally, we had some fun with the laser cutter. Well, I had fun with the laser cutter. I hope you had fun watching me have fun with the laser cutter. Over on Element 14, I'll provide links to the design files, the code, and some stuff on capacitive touch technology. While you're there, why don't you leave a comment and let me know what you would have done differently in your build. For now, my name is James and I'm the Bald Engineer. I'm gonna start counting my coins now. While I do that, check out this clip I made. Who needs a flying car when you have a space portal? I want to thank you for coming to watch my very first Element 14 Presents video. This has been a lot of fun. I'm looking for... Oh, sorry, I don't feel so good. Oh no, I just got here.